All right, let's unpack this. Have you ever really thought about what truly underpins every single line of Java code you write?
Yeah.
I mean, beyond the frameworks, beyond the libraries, there's this definitive blueprint, right,
Oh,
that makes it all work.
exactly. It's the absolute foundation. It guarantees consistency, predictability across every Java environment. It makes sure your code behaves the same way, whether it's on your machine or deployed globally.
And today, our mission is, well, to embark on an exclusive guided deep dive into that very blueprint, the Java Language Specification, the 24th edition. Imagine we're taking you on a tour, kind of as if the primary author themselves, the very person who crafted these rules, is walking us through their notes for advanced developers.
Right. We'll try to distill those, let's be honest, incredibly complex rules into clear, actionable insights. We'll simplify the challenging concepts with real-world scenarios, highlight the really critical changes that affect modern Java, and maybe even anticipate those gnarly questions that pop up when you're truly digging deep into the spec.
Yeah, the goal is that you'll walk away not just informed, but genuinely well-informed. Equipped to tackle the toughest interview questions, design truly robust, resilient systems, or maybe even contribute to the language's evolution. Let's get started. Okay, so we begin our journey at the absolute granular level, how Java recognizes the smallest, most fundamental pieces of your code. Think of it like understanding the individual atoms before you even think about building molecules.
That's right. The JLS meticulously defines Java's lexical structure,
Yeah.
starting from the raw stream of Unicode input characters all the way to the tokens the compiler actually sees. This initial stage, often overlooked, it really dictates everything that follows.
It's astonishingly precise, too. Take Unicode escapes, for example. Did you know that the raw input U005 Go05A
Yeah.
that results in 6 separate characters, backslash U005, A, not the letter Z? Because that first backslash from the Unicode escape isn't then reinterpreted as the start of a new escape sequence.
Exactly. And that other tricky one with string literals, the raw input looks simple, but it actually results in the where that final backslash and n are interpreted together as a line feed character.
So why? Why such intricate rules for backslashes and Unicode processing?
Well, it's fundamentally about ensuring a deterministic translation of your source code. It has to be predictable. These rules iron out any ambiguity right at the beginning, in the earliest processing steps, even before tokenization happens. It's crucial for compilation consistency.
And then there's the longest possible translation rule. It's subtle but powerful, like public static is always seen as one single identifier, always, never as two separate keywords, public and static. If you want both, you absolutely need a separator space, comment, something.
hmm This rule is essential. When we were designing Java, predictable parsing was, well, a cornerstone of its robustness. Without it, you could have accidental syntax errors leading to vastly different interpretations of the exact same code. The JLS aims to prevent precisely that.
Okay, let's touch on identifiers too, the names we give things. Java is pretty impressive here, embracing the entire Unicode set. So you can have names like Arty. But there's a key rule. An identifier can never, ever have the same spelling as a reserved keyword, like class or int.
Right. But it can match a contextual keyword, things like yield or record. Their meaning depends entirely on where they appear in the program. They're not reserved everywhere.
Speaking of keywords, the JLS explicitly lists const and goto as reserved, even though Java doesn't use them. Why is that?
That was a deliberate design choice, actually, mostly to help C++ developers who are migrating to Java. It lets the compiler give much clearer error messages if they accidentally use those familiar keywords.
Makes sense. Okay, literals how values are directly represented. We've got binary hexadecimal floating point numbers
Right.
and that surprising integer literal limit, 21474836848, which is 2 to the 31st power. It's unique, right? It can only appear as the operand of the unary minus operator.
That's the only place. Anywhere else, it's a compile time error. And remember, standard floating point literals are double by default. You need that F or F suffix if you want to float.
What about nan?
Yeah, not a number. It's handled very specifically. Float.nan and double nan are explicitly predefined constants in their classes. It reflects Java's strict adherence to the IEEE 754 standard for floating point math. It helps prevent pitfalls with undefined numerical results.
Okay. And character literals. They're limited to UTF-16 code units, so supplementary characters need surrogate pairs. And that common pitfall, I'll say for a line feed.
Won't work. You need blim. Because those Unicode escapes are processed so early, this actually becomes a line feed character in the source, breaking the single line literal rule.
Huh?
Same for Mayo 27 for an apostrophe.
Got it. And string literals, the JLS guarantees they're interned, right?
Yes, if they are constant expressions. This means they always refer to the same instance of java.lang_string, which has big implications for comparisons. Remember, system.out.print on the mlen, held plus low.
Right, it prints true. Because both sides are constant expressions resolving to the same interned string. Okay, now a big one. New in JLS 24. Text blocks. Introduced with the triple double quotes.
We need to explore their structure, how line terminators are handled, leading trailing white space, and that critical string.translate escapes processing step. There's that tricky example where a stray double quote at the very end can cause an error.
Oh, so?
Because the first 3 consecutive double quotes on the last content line are taken as the closing delimiter. If there's another quote after that, it's just left hanging, causing a syntax error.
Ah, subtle. So understanding these foundational lexical rules is pretty important then.
It's paramount for advanced developers, really. It prevents obscure bugs that start literally at the character level. It helps if you're writing code generators and ensures compatibility when you're integrating with older systems or parsing code. It's step 1 to true mastery.
Okay, so we've dissected the atoms. Now let's elevate our view to the molecules, how those characters come together into the fundamental types, values, and variables. The bedrock of Java programs.
Right. The JLS makes a very clear distinction between primitive types like int, float, boolean, which hold the exact value, and reference types, objects, and arrays, which hold essentially pointers to objects or null. This is fundamental to Java's memory model and its object-oriented nature.
And here's where Java gets interesting, maybe a bit strict. The Boolean type. Unlike C, where 0 might be false and non-zero true, Java says no. Explicit checks only. You can't treat an int 0 as false or a null object reference as false. You absolutely need x, 0, or objacus null.
So why the strictness? Why did we design it that way? It was deliberate. For safety and clarity, it prevents a whole class of common type-related errors. It forces explicit conversion or comparison, eliminates ambiguity, makes your intent crystal clear.
Okay, and variables are essentially typed storage locations. Primitive variable holds the value itself. Reference variable holds null or a pointer.
Exactly. And connecting this to the bigger picture, object really is the universal superclass type. A variable declared as object can hold null, or a reference to any object, a class instance, an array, anything. It's the root of the hierarchy.
That Boolean difference between Java and C is definitely a classic point to remember. Okay, let's go even deeper now into the type system, especially looking at advanced patterns, generics, variable nuances.
Right. And a particularly fascinating, often misunderstood area, raw types.
What?
If you use a generic class, say outer T, but you use it without its type argument, just outer, then any inner class, like outer, inner, also implicitly becomes raw, meaning you can't then pass type arguments to inner either, something like outer. Inner double x equals null becomes illegal if outer itself is used raw.
Okay. And this leads us straight into heap pollution.
Yeah.
Critical concept, right? Comes up a lot.
Oh, absolutely. It's a notorious source of runtime class cast exceptions, especially when you mix generic and non-generic code or deal with legacy APIs.
Can you give us those JLS examples?
Sure. First one. List L equals new array list number. List string L equals L. You get a compile time unchecked warning, okay? But at runtime, L's actually refers to a list number, not the list string you declared it as. That's the pollution.
Okay, example 2.
Right. Static void M, list strict array string lists, list integer templist arrays.asList 42, array integer templist string S, string lists 0.get0, boom. Runtime class cast exception. Why? String lists is a list string, but you alias it as object. That lets you sneak a list integer into it. Then when you try to get a string back out, exception.
So what's the takeaway here? Why allow raw types at all if they cause this?
Well, the JLS is clear. Raw types were a pragmatic compromise, essential for backward compatibility with all the pre-generics code out there. But they acknowledge they can be deliberately unsound in their type rules. It was discussed way back in '98, making the future safe for the past. They enable interoperability, but with a known risk.
So avoiding heap pollution is paramount then.
Absolutely. For type safety, for preventing those nasty runtime surprises in complex apps, it shows the limits of static typing when you work around generics.
We should also briefly mention intersection types, like T1 and Tn.
Right. They pop up from type parameter bounds like T extends, runnable, and serializable, or in cast expressions. The JLS talks about a notional class or interface. What that means is it's a conceptual thing for the compiler. It helps the compiler figure out which members are available when you combine multiple types. It ensures type safety without actually generating extra bytecode at runtime.
And subtyping. That defines the IS relationship.
Exactly. The JLS has explicit rules like object-object and clonable object that shows Java's array covariance. An array of object can hold references to arrays of any reference type.
Okay. And the 8 kinds of variables.
Yeah. Class variables, static, instance variables, array components, method parameters, constructor parameters, exception parameters, and local variables, including the new pattern variables. They each have their own lifecycle and initialization rules.
How does Java make sure local variables are initialized?
Through definite assignment rules. We'll cover those in detail later. Basically, the compiler proves it's assigned before use. And crucially, remember, type erasure, type variables and arguments aren't reified at runtime. A single class object might represent many compile-time generic types.
Good points. For deeper study, explain heat pollution, raw type, erasure, and give an example of an intersection type. All right, let's shift gears now to how Java handles changes in type. It's not just about explicit casts. It's a whole system of conversions, often implicit, guided by strict rules.
Exactly. We distinguish between widening primitive conversions like float to double. These never cause a runtime exception, even if you lose some precision. Then there are narrowing primitive conversions long to int, for instance. These can overflow or underflow, but they also never throw an explicit runtime exception. The bits just get truncated.
There's that unique one that combines both.
Right. Byte to char. It's a two-step dance. First, the byte widens to int, then that int narrows to char. Ensures the value fits into the 16-bit char.
Okay. What about reference types?
Widening reference conversions subtype to supertype are checked at compile time. They're guaranteed safe. But narrowing reference conversions supertype to subtype, that's where the runtime checks happen. Potentially a class cast exception. That's Java's safety net catching you.
Can you give that JLS example again, the point one?
Sure. Casting P, a point object, to colored point like CP, colored point P, that might work, or it might fail at runtime, depending on what P really is. But trying to cast that same point P to long L, long key, that's a compile time error. The compiler knows it can never succeed because they're unrelated types.
Got it. Unboxing, unboxing, integer to int, etc.
Yeah, the JLS gives JVM implementers some leeway here. Implementations may cache identical object references for common values, like small integers. Integer.value of 10 might always return the same object. But you, the programmer, should never assume identity using for all boxed values. It allows optimization, but doesn't guarantee it everywhere.
Okay. And capture conversion. That sounds complex.
It's subtle, but really clever. It lets you safely pass something like a list of unknown type, to a method expecting a list T. The compiler infers and captures that unknown type into a temporary hidden type variable T just for that call. This allows flexible APIs, like a reverse method that works on any list, to maintain strict type safety internally.
Why is it harmless, as the JLS says?
Because you're guaranteed the incoming argument is a list of some type, even if you don't know which one at the call site. Capture conversion creates a temporary, strongly typed context for the method body, preserving safety without making the API rigid. It's a key piece of the generics puzzle.
Good explanation. For notes, define widening primitive conversion, narrowing reference conversion, boxing, and capture conversion. All right, let's move into the absolute core of object-oriented Java classes themselves. Chapter 8 details their anatomy, behavior, the real backbone.
Indeed. Class declarations start with critical modifiers. Abstract, for example. An abstract class basically mandates that all its abstract methods must be implemented by some concrete subclass down the line. Otherwise, it's a compile time error.
And a huge one, new in JLS 24. Sealed and non-sealed classes and interfaces. This is a game changer, right?
Absolutely. A sealed class explicitly lists its permitted direct subclasses using the permits clause. It gives you precise control over who can extend your class. Conversely, a non-sealed class must have a sealed direct superclass or super interface. It acts as a designated point where the hierarchy can be opened up again for wider extension. This really helps maintain invariance and allows the compiler to reason about exhaustiveness, especially with switch.
And records.
Right. A record class is implicitly final, cannot be subclassed. And if it's nested inside another class, it's implicitly static. No hidden outer instance needed. These defaults simplify things and enforce the idea that records are primarily simple data carriers.
Okay, fields. The difference between static and instance variables.
Static fields are class variables. Only one copy exists, shared by all instances of the class. Created when the class is initialized, instance variables are non-static. Each object gets its own separate copy when the object is created.
And volatile, crucial for concurrency.
Absolutely critical. Volatile guarantees memory visibility between threads. A write to a volatile field by one thread is guaranteed to be seen by subsequent reads by other threads. But, and this is vital, it doesn't guarantee atomicity for long and double operations on its own. You might still need extra synchronization. The JLS has that classic example, I++ and J++ without synchronization. J might end up greater than I due to reordering. Volatile fixes visibility, not atomicity of compound actions.
Okay, instance and static initializers. Those blocks outside constructors.
Yeah, code blocks for initialization. They have restrictions, like no return statements. Static initializers run when the class is initialized. Instance initializers run just before the constructor body for each new object.
Method declaration. Let's start synchronized.
The main tool for thread safety, for instance, methods, synchronize automatically locks on the instance. For static methods, it locks on the class object itself. So the difference between synchronized void bump and static synchronized void class bump. One locks the specific object, the other locks the entire class. Huge difference in concurrent scenarios.
And the throws clause for checked exceptions.
A cornerstone of Java's error handling. If a method or constructor might throw a checked exception, it must either catch it or declare it in its throws clause. Forces you to think about error paths.
Overriding versus overloading. The line buffer output example.
Yes, a beautiful demonstration of dynamic dispatch or polymorphism. A method called in a superclass, puchar, can actually execute the overriding implementation from the current object's actual class, puchar. It doesn't necessarily run the version defined in the superclass itself. It depends on the runtime type of the object.
Enum classes.
Implicitly extend enumi. The constants are implicitly public static final fields. You get handy methods like values returning an array of all constants and value of string name.
And another major JLS 24 feature. Record classes.
Huge. So concise for data carriers. Implicitly final, implicitly static if nested. They automatically get implicit private final fields for their components. Plus, automatically generated canonical constructors, normal and compact forms, and default equals, hashcode, and toString methods based directly on the components.
How do they simplify things but also enforce rules?
Well, they dramatically reduce boilerplate, but they also impose restrictions. No non-static fields other than the components, no abstract or native methods, no instance initializers. And crucially, their equals method looks directly at the component field values, not accessor methods. This enforces structural equality and data integrity.
Constructor declarations. Creating instances.
It's essential for constructor chaining.
Yeah.
This one calls another constructor in the same class. So super calls a superclass constructor, ensures the whole initialization chain happens correctly.
What's the precise order during object creation? This seems important.
It is, and often tested. First, memory allocation. Second, fields get default values, 0, null, etc. Third, constructor arguments evaluated left to right. Fourth, constructor body invoked. And critically, the out-of-memory error check happens before argument evaluation. If allocation fails, the arguments aren't even touched.
And that classic interview question, dynamic dispatch during construction.
Right, the JLS super and test example. If a superclass constructor calls a method that the subclass overrides, the subclass's overriding version gets invoked even before the subclass's own field initializers have run. So a field might print its default value, like 0 for an int, inside that method instead of the value it gets assigned later in the subclass initializer. Very subtle.
Definitely subtle. For study. Explain sealed class, record class implicit features, volatile field memory visibility, and dynamic dispatch during construction. Interfaces have really evolved, haven't they? Let's explore their modern capabilities. They're much more than just contracts now.
They really have. Interface declarations now also support sealed and non-sealed, just like classes. An interface with a sealed direct superinterface must itself be declared either sealed or non-sealed. It keeps that explicit control over the hierarchy.
Interface members. Fields are always public static final. Implicitly. But the methods. That's where the big changes happened.
Absolutely. Since Java 8, interfaces can have default methods with bodies, providing default implementations, private methods, helper methods within the interface, and static methods, utility methods associated with the interface. This is huge. It allows interfaces to evolve, adding new functionality without breaking all existing implementing classes across the ecosystem.
Let's talk annotation interfaces too.
Right. You define annotation types using @interface. You can define elements, which are like methods, and provide default values for them. And for frameworks, repeatable annotations are key. They let you apply the same annotation multiple times on a single element, managed via a special containing annotation interface.
The JLS explains predefined annotations like @override. What's the nuance there?
It's insightful. @override is allowed on interface methods that are override equivalent to public methods of object, like hashcode or equals, but you cannot put @override on an interface method intended to override object.clone because object.clone itself isn't public, shows the precision of the rule.
Okay. @suppress warnings.
Used to suppress specific compiler warnings, common strings are unchecked for generics issues. Deprecation, removal, and new in JLS 24 preview for warnings about using preview language features. And at safe_vargs, which is interesting because it has non-local effects, it suppresses unchecked warnings at the call sites of the vargs method, not just at the method declaration.
And finally, function types.
Yeah, the types associated with functional interfaces. The JLS notes some aspects, like the order of thrown types in the throws clause, are defined non-deterministically, but it clarifies this non-determinism does not matter for practical use, a key point. Generic functional interfaces can be implemented by method references, but you can't write generic Lambda expressions directly. There's just no syntax for it.
Good to know. Flashcard prompt. List the types of methods an interface can contain and explain repeatable annotation. Okay, chapters 6, names. Every single thing in Java code has a name, and how these names are resolved, their scope, their interactions. It's all meticulously defined. It's how the compiler figures out what X you're talking about.
Exactly. The JLS carefully differentiates a simple name, a single identifier like X, from a qualified name like package.class.field or object.method. It also clarifies that sometimes an identifier is just part of a declaration, like test in class test, while other times it's a name referring to something already declared, like string in string s.
Like args.length versus args.length.
Precisely. args.length is a qualified name accessing the length field, but an args.length is just an identifier used within a method invocation expression. Different grammatical roles.
Scope is crucial. What about that shadowing example? int x is x.
Classic compile time error, because the local x on the right-hand side is used before it's been definitely assigned a value by the declaration itself. But contrast that with int x, x22. That works. Why? Because the assignment x2 within the parentheses definitely assigns x before its value is needed for the multiplication, shows the compiler's flow analysis.
And new in JLS 24, expanded rules for scope for pattern variables in statements.
Yes, like in if ofcs of string s is explicitly defined to be in scope only within the then block where the type test is guaranteed to have passed, not in the else block. This ensures type safety is maintained precisely where the pattern variable is meaningful.
Shadowing and obscuring. Why are these important?
For clarity and preventing ambiguity. For example, you can't redeclare method parameter as a local variable inside the method body. That would be shadowing and confusing. Field names can shadow or obscure type names, less ideal but allowed, but they can't obscure method names. These rules help keep name resolution predictable.
And access control public, protected, private, default package. Fundamental for encapsulation.
Absolutely. And the rule for protected is particularly specific, often misunderstood. Access to a protected member declared in Class C is permitted from within a subclass S, but only when accessing the member via a reference whose compile time type is S or a subclass of S. The JLS examples clearly show how protected and package access strictly limit visibility across package boundaries.
Okay, Quizlet idea. Distinguish identifier versus name, explain shadowing, and describe the precise rule for protected access. And moving on to structure. Packages and modules. Java programs aren't just flat lists of classes, they're organized hierarchically.
Right. Packages provide namespaces, preventing naming conflicts. The JLS recommends unique hierarchical names like com.yourcompany.yourproject, especially for code meant to be shared.
And the big addition, new in JLS 24, modules. This is about strong encapsulation and managing dependencies explicitly.
Exactly. A module declaration, module-info.java, categorizes its packages. Some are exported, meaning their public types are accessible outside the module. Others are internal, hidden. This gives much finer-grained control over your API surface than just packages alone.
What's the crucial difference between exports and opens in module-info.java?
Good question. Exports grants compile time and runtime access to the public and protected types and members of a package. Standard visibility rules apply. Opens, however, grants reflective access at runtime to all types and members within the package, even private ones. This is mainly for frameworks that need deep introspection.
Can you restrict who gets access?
Yes, both exports and opens can have an optional to clause, followed by specific module names. This creates friend modules, granting access only to them, not universally.
Interesting nuance. What if you try to export or open a package that doesn't exist in the current module?
It's a compile time error if you try to export a package your module doesn't contain. Makes sense, you can't export what you don't have. But it's permitted to opens a package that isn't in the current module. In that case, the opens directive simply has no effect. It allows for more flexibility in configurations where modules might conditionally contain packages.
And packageinfo.java.
That's the special file solely for putting package-level annotations.
Got it. Flashcard prompt. Compare exports versus opens directives in modules. Chapter 10, Arrays. Fundamental, yes, but the JLS reveals some surprising details about their exact nature.
Definitely. First key thing, arrays are objects. They are created dynamically at runtime, they live on the heap, and you can assign them to variables of type object. They implicitly inherit methods from object like toString equals hashcode, and they implicitly implement clonable and java.io serializable.
So what's the difference between just declaring in I and actually creating the array?
Big difference. In I just declares a variable named I that can hold a reference to an integer array. It doesn't create the array itself, doesn't allocate memory for elements. To actually create the array object, you need an array creation expression, like AI equals new in 10.
Yeah.
That allocates space on the heap.
How are array classes represented? Like in .class.
Fascinating bit. Calling getClass on an int object returns a special class object represented internally by the string I. For string, it's java.lang string. And importantly, two different array objects of the same primitive component type, e.g. two different int arrays, will share the exact same class object at runtime. An optimization.
Crucial point for interviews.
Yeah.
Char is not a string.
Absolutely not. They are distinct types. String is immutable, has a rich set of methods. Char is a mutable array of characters. Totally different behavior and representation. Never confuse them.
Okay, array access. Array index. What about evaluation order if the array is null?
The JLS is precise here. The index expression is fully evaluated first. Then the check for a null array reference happens. So in that example, nada index 2 plus plus where nada returns null. The assignment index 2 will happen. Then the JVM tries to access the element of the null array, and that's when the null pointer exception is thrown. The index evaluation completes before the NPE.
Good to know. Quizlet idea. List 3 properties of Java arrays. Explain the difference between char and string. Chapter 11. Exceptions. Graceful error handling is vital, and Java's exception mechanism is a cornerstone of its safety.
Indeed. The JLS distinguishes between synchronous exceptions, those resulting directly from a specific program action, like division by 0 or a null pointer access, and asynchronous exceptions, which can occur almost any time, conceptually. The classy example was thread.stop, which is deprecated precisely because it's asynchronous and can leave objects in inconsistent states. Crucially, all exceptions in Java are precise. This means all side effects of statements before the point where the exception occurred are guaranteed to have taken place. The program stays consistent up at that point.
And the really interesting part for developers, compile time checking of checked exceptions.
Yes, this is a major design choice in Java. If a method can throw a checked exception, like IO exception, you must either handle it with try-catch or declare it in the method's signature using throws. It forces developers to explicitly acknowledge and plan for potential error conditions, which significantly improves code robustness and maintainability.
How does the compiler figure out what exceptions a specific throw statement can throw?
It's quite specific. For a statement like throw new file not found exception, the compiler knows that this specific statement can throw only file not found exception. It doesn't automatically consider its superclasses, like IO exception, or any potential subclasses as being thrown by that exact statement. The analysis is per statement, though the overall method signature considers all possibilities.
Okay, flashcard prompt. Define precise exception. What is the purpose of compile time checking for exceptions? All right, chapter 12, execution. Let's peek behind the curtain at what happens when your Java program actually runs inside the JVM from startup to shutdown.
It's a well-defined sequence. The JVM startup involves three main phases for each class or interface as needed: loading, linking, and initialization. It's a systematic process.
Tell us about loading.
Loading is about finding the binary representation, the .class file usually, and creating a class object to represent that type within the JVM's memory. This can fail, right? With things like class circularity error, A needs B needs A, class format error, bad bytecode, or no class defounder, found at compile time, missing now. And yes, even out-of-memory error can happen during loading because creating that class object and related structures requires memory.
And class loaders need to be consistent.
Absolutely critical. A given class loader, when asked for the same class name twice, must return the exact same class object. This prevents security holes and ensures type identity. You can't have two different definitions of the same class loaded simultaneously by the same loader.
Okay, after loading comes linking. What happens there?
Linking has three steps itself: verification, checking bytecode validity, type safety, preventing stack overflows, etc. Preparation, allocating memory for static fields and setting them to default values. And resolution, finding and linking symbolic references in the code to actual memory locations or methods. Resolution can be lazy done only when a reference is first used or eager done earlier. Depends on the JVM implementation.
What errors can pop up during linking?
You might see instantiation error trying new abstract class, no such field error, or no such method error if code is compiled against one version of a library but runs against an incompatible later version where something was removed, or unsatisfied link error if a native method implementation can't be found.
Let's revisit instance creation order. It seems crucial.
It is, especially for tricky interview questions. Order: 1. Allocate memory. 2. Initialize fields to defaults, 0, null. 3. Evaluate constructor arguments left to right. 4. Invoke constructor body. And remember, the out-of-memory error check for step 1 happens before step 3. Arguments aren't evaluated if memory allocation fails.
And dynamic dispatch during creation. That test example again.
Yes, the super in test example. If the super constructor calls a method M, and test, the subclass, overrides M, then test's version of M is called from the superconstructor. This happens before test's own field initializers run. So if M prints a field initialized in test, it will print the default value, 0 from step 2, not the value assigned later in test's initializer, like 3. It highlights the exact sequence.
What about finalization?
Finalization, finalize method, gives objects a chance to clean up resources before garbage collection. But the JLS is very clear. The order of finalizer calls is unspecified, and relying on it is dangerous. Modern Java encourages using try with resources or cleaner instead. The JLS also defines definitely reachable objects to guide GC.
Got it. Quizlet idea. List the three main phases of JVM execution. Explain dynamic dispatch during instance creation. Chapter 13. Binary compatibility. One of Java's big promises, right? But what does it really mean and what are the limits?
Right. And the first crucial point: binary compatibility is not the same as source compatibility. They're different concepts. The JLS gives an example. You can have a set of .class files that run together perfectly fine, binary compatible, but the original .java source files might not compile all together anymore if, say, adding a new class changed the meaning of a name used in existing code.
So how can you evolve code while maintaining binary compatibility? That colored point example.
Ah, yes. If you have a point class with method adopt, point P, and later you add an overloaded adopt, colored point CP, to a subclass colored point, older code compiled only against point might still resolve calls to the original adopt, point P, even when past a colored point, potentially breaking if it relied on the new method's behavior. Recompiling the client code fixes it, but the old binary might break. Shows the subtleties.
What about inconstant constants, static final fields?
This is a really important practical point from the JLS. It strongly recommends using static final only for values that are truly fundamentally constant, like math.py. Why? Because the compiler often inlines the values of static final fields directly into the bytecode of classes that use them. If you later change the value of that constant in the library, the old client code won't see the change unless it's recompiled. It still has the old value baked in. Better to use a private static field with a public static getter method if there's any chance the value might change later.
And changing a class from non-final to final.
That can definitely break binary compatibility. If someone wrote a subclass extending your original non-final class, their compiled subclass bytecode now references a superclass that is no longer extensible. Loading that subclass will likely cause an incompatible class change error.
Good warnings. Flashcard prompt. Differentiate binary compatibility from source compatibility. Explain inconstant constants. Chapter 14. Blocks, statements, and patterns. This is about control flow, how the program makes decisions, loops, and now how it uses patterns.
Right. The JLS defines statements rigorously. It even tackles the classic dangling else problem grammatically. It categorizes statements to ensure an else always binds to the nearest preceding if that doesn't already have an else. No ambiguity.
Assert statements, assert condition, message.
Compile time configurable. If assertions are disabled, the default runtime behavior, neither the condition expression nor the optional message expression is evaluated at all. Zero runtime cost. Great for internal consistency checks during development and testing.
Now, the big enhancements in JLS 24. Switch statements and expressions with pattern matching.
Huge improvements. We now have the concept of exhaustiveness checking for switch. If you switch on an enum or a sealed class interface or use record patterns, the compiler can often determine if you've covered all possible cases. If you have, you might not need a default label anymore. This guarantees completeness and catches errors at compile time.
Can you have multiple default-like labels, like case null and an untraditional pattern?
Nope. A switch block can have, at most, one label that effectively acts like a default, catching everything not caught by more specific preceding cases. This includes case null, default, or a pattern like case object O. Keeps the logic clear.
Why doesn't iPair AAA, iPair BBBB, iPair CCCC exhaust iPair IIJ, according to the JLS example?
That's subtle. It's because combining record patterns only works if they match the same values in the other components. Here, the patterns AABBCC are different for the second component as well. The compiler can't guarantee that covering A, B, C, C covers all possible combinations like A, B, or B, C, etc., when I could be A, B, or C.
Okay, and the yield statement.
Used specifically inside switch expressions, not statements, to provide the value that the entire switch expression evaluates to for a given case.
Unreachable statements. Always an error.
Usually. The JLS definition is precise, while false by 3 is a compile time error because the statement by 3 is provably unreachable. But interestingly, if false by 3 is not an error, why? Because the if statement itself is reachable, even if its body isn't executed. The statement by 3 isn't considered unreachable in the strict JLS sense, allows for conditional compilation using final Boolean flags.
And new in JLS 24, pattern matching goes beyond switch.
Oh yes. Instance of now supports patterns. If object instance assuming S, use S. It tests and binds the variable in one go. Record patterns let you destructure records directly. If object instance of point in X and Y, use X and Y. And we have unnamed pattern variables to elegantly ignore components you don't need in a pattern match.
Lots of powerful new tools. Quizlet idea. Define switch exhaustiveness, yield statement, pattern variable, and contrast unreachable statement rules for while versus if. Chapter 15. Expressions. The real workhorses doing the calculations. Understanding their evaluation order, types, nuances. Crucial.
Absolutely. Java meticulously defines operator precedence and associativity. Guarantees predictable results like I3I. It's always 9. The assignment I3 happens fully before the multiplication uses the new value of I, strict left-to-right evaluation of operands before the operation.
Floating point arithmetic always has curves.
It does. For example, because of NaN, ORCC is not always equivalent to XY. Comparisons with NaN always return false except for dumbig. And due to potential overflow, underflow, or precision issues, 4.0 by 0.5 might not yield the same result as 2.0x for all floating point values x. Care is needed.
The JLS warns about reordering floating point calculations.
Explicitly. Because floating point math isn't always computationally associative like integer math, naive reordering can change the result. Also, Java's percent operator for floats acts like integer remainder, which is different from the remainder operation specified by IE 754, which you can find in math.ie remainder.
Method invocation. How does Java pick the right overloaded method?
Through a complex overload resolution process. It finds all applicable methods and then picks the most specific one based on the argument types. Crucially, the return type is not considered during this selection. The JLS test colored point P example shows this. Even if a method with a different return type would be a valid assignment target, it won't be chosen if another method is more specific based purely on argument types.
Why ignore the return type? Seems counterintuitive sometimes.
It's a deliberate design choice to simplify overload resolution and avoid ambiguity. If return types were considered, you could easily have situations where multiple methods seem equally specific, making the choice unclear or context-dependent. Sticking to argument types makes it more predictable.
Method reference expressions. Class name.static method, object.instance method.
Powerful shorthand, evaluated at runtime, similar to creating objects, key difference from direct invocation. Using a method reference with a null primary object, like null.shareString, always throws a null pointer exception. This differs from calling a static method like string null.value of 1, where the null on the left is ignored because the method is static.
Lambda expressions.
Mm-hmm.
Runtime behavior.
Interesting point. The identity of the object resulting from evaluating a lambda expression is unpredictable. Might return true or false for two evaluations of the same lambda. You shouldn't rely on lambda identity. They represent behavior, not specific objects. A new object isn't guaranteed for each evaluation.
Constant expressions. Why are they special?
They are expressions denoting a primitive value or a string that can be evaluated at compile time, don't complete abruptly, and are composed only of literals, specific operators, plus makes it, etc. on primitives, and references to other constant variables. This compile time evaluation is precisely why string literals, which are constant expressions, can be interned by the JVM, saving memory by sharing identical instances.
Okay, Quizlet idea. Explain why 4.0 post 0.5 isn't always 2.0x. Why is return type ignored in overload resolution? What's the key difference in NPE behavior between method invocation and method reference with a null primary? Chapter 16, definite assignment. Another key part of Java's safety net, enforced at compile time.
Exactly. It's a static analysis the compiler performs. What it guarantees is that every local variable and every blank final field, the final field without an initializer where it's declared, must be definitely assigned a value on every possible execution path before its value is accessed.
Can you give those examples again, the final int k ones?
Sure. This compiles final int k if flag k else k for y, because k is guaranteed to be assigned exactly once whether flag is true or false.
Right.
But this doesn't compile final int k if flag k3 if.flag. Why not? Because the compiler sees two separate if statements. It can't guarantee that one and only one of them will execute. If k were used after these ifs, it wouldn't be definitely assigned.
Why is the compiler so strict about this? Seems overly cautious sometimes.
It's a deliberate design choice, again focusing on safety. It completely prevents errors caused by using uninitialized local variables, which are a notorious source of hard-to-find bugs in languages like C or C++. Java trades a little flexibility for guaranteed safety here.
Makes sense. Flashcard prompt. Define definite assignment. Provide an example where definite assignment rules prevent a compile time error, or allow compilation. Chapter 17. Threads and locks. The Java memory model. For advanced concurrent applications, this is non-negotiable, right?
Absolutely non-negotiable. If we connect this to the bigger picture, the JLS rigorously defines the contract between threads and main memory. It ensures consistent behavior across wildly different hardware architectures and compiler optimizations. It's Java's bedrock for concurrent programming.
Synchronized statements and methods are the main tools here.
They are the primary built-in mechanisms. They ensure mutual exclusion using monitors, locks. A thread performs a lock action before entering the synchronized block method, and an unlock action when exiting, even if via an exception. Crucially, synchronized also establishes memory visibility guarantees between the unlock of one thread and a subsequent lock by another thread on the same monitor.
Yeah, the really tricky part, data races. That JLS example.
Yes, the classic demonstration of why synchronization is vital. Thread 1 does B1, A equals 2. Thread 2 does R2, R1 equals B. Without synchronization, the memory model allows reordering. It's possible, perhaps counterintuitively, for thread 2 to read the initial values, resulting in R1 and R2 This might seem broken, but it's allowed by the JMM if there is a data race, unsynchronized access to shared non-volatile variables where at least one access is a write.
This leads directly to the happens before relationship.
The core concept. It's a partial ordering of actions in the program. If action X happens before action Y, then the results of X are guaranteed to be visible to Y. Examples: an unlock on a monitor happens before subsequent locks on the same monitor. A write to a volatile variable happens before subsequent reads of that same variable. Thread start happens before any action in the started thread.
The JLS also mentions default initialization happens before other actions.
Yes. The default initialization of all fields to 0, null, false, when an object is allocated happens before any other action in the program except other default rights. Guarantees you never see garbage values, only defaults or properly initialized values.
Final field semantics. These seem powerful.
Very powerful guarantees. If an object's constructor initializes its final fields, and that object is then safely published, for example, assigned to a volatile field, returned from a synchronized block, put into a concurrent collection, then all other threads that subsequently access that object are guaranteed to see the correct initialized values of those final fields. The JLS final field example shows this. FX final will always be seen as 3, but FY, non-final, initialized in the same constructor, could be seen as 0 by another thread if F isn't safely published, due to reordering.
What about changing final fields later, maybe with reflection?
The JLS acknowledges this is possible, but strongly advises against it. It should ideally only happen before the object is made visible to any other thread. The spec also defines final field safe context to provide stronger guarantees, even in the face of such modifications, crucial for certain low-level library code.
Lastly, atomic transactions. Reads and writes.
Reads and writes of references are always atomic. Reads and writes of all primitive types except long and double are also always atomic. However, reads and writes of long and double are not guaranteed to be atomic without using volatile or locks. A JVM may perform them as 2 separate 32-bit operations, potentially leading to torn reads, where a thread sees half of one value and half of another if there's a concurrent write.
Critical details. Quizlet idea. Explain data race. Happens before relationship and final field semantics. Okay. Chapter 18. Type inference. The compiler doing clever work behind the scenes to make generics easier to use.
It really is quite sophisticated. The compiler figures out the type arguments for generic method calls or diamond operator instantiations. It involves a complex process based on constraint formulas, involving steps called reduction, simplifying constraints, incorporation, adding new bounds based on context, and resolution, determining the final concrete types for the inference variables.
So list number ln, arrays.asList1 2.0, just works because
the compiler infers the type parameter t for arrays.asList based on the arguments 1 integer and 2.0, double. It finds the most specific common supertype, which in this case resolves to something like number incomparable. So it figures out you want a list number without you explicitly writing number as list.
the JLS calls the process rather complex. Why?
Because it needs to handle intricate scenarios involving wildcards, bounds, target types, and method overload resolution, all while maintaining rigorous type safety. It's a balance between powerful inference and correctness, which inevitably leads to complexity in the rules.
Makes sense. Flashcard prompt. What are the 3 main processes of type inference mentioned in the JLS?
Okay, so if I were to step into the shoes of the JLS primary author for a moment and give you the narrative, the heart of this specification for advanced developers, here's how I'd frame it. Fundamentally, Java is designed as a high-level, implicitly safe language. That's key. We deliberately included automatic storage management, the garbage collector, precisely to avoid the huge safety problems you see with explicit memory deallocation, like dangling pointers or double freeze in C or C++ array. Our commitment to safety means we disallowed fundamentally unsafe constructs. You won't find pointer arithmetic. Array accesses are always checked. This core philosophy, this focus on safety and predictability, really drives so much of the language's design. We start the specification with lexical structure because precision right down at the character level is paramount. Understanding tokenization, how Unicode escapes are handled before anything else, that longest possible translation rule, that's not just academic. It dictates how the compiler even sees your source code. Similarly, the strictness of Boolean, the specific behaviors of literals, they're all part of this larger design goal. Predictable, unambiguous, program behavior. We wanted to prevent subtle bugs that start from the very first characters you type. Now, the type system, especially generics, represents a major evolution. Concepts like raw types and type erasure, well, those were pragmatic, necessary choices. We had to ensure backrow compatibility with the vast amount of pre-generics Java code out there. But you, the advanced developer, absolutely must grasp heat pollution. You need to understand its causes, its consequences, because it represents a deliberate, documented loophole in an otherwise strongly type-safe system. It's where class-cast exceptions can sneak in at runtime. And capture conversion, that's the sophisticated machinery that allows the flexibility of wildcards while still maintaining type safety internally. It lets you write more adaptable APIs. Looking at the new features in JLS 24, things like record classes and sealed class interfaces, these are powerful tools. They're designed to help you write more robust, more expressive, more maintainable code. They let you explicitly define the shape of your data carriers with records and precisely control inheritance hierarchies with sealed types. These aren't just syntactic sugar. They encode important design patterns directly into the language syntax, allowing compilers and tools to better understand and enforce your architectural intent. Then there's your code's journey through the JVM loading, linking, initialization. It's a complex dance, yes, but understanding the guarantees and the potential pitfalls at each stage, like the different kinds of linkage errors, or knowing exactly when an out-of-memory error might occur during startup, before constructor args are evaluated. That's vital for debugging the really tough production issues. And finally, for concurrent programming, the Java memory model is your definitive guide. It is not intuitive. It's a precisely defined formal contract between the JVM and your code and between threads. Grasping concepts like data races, the happens before relationship, and the surprisingly strong guarantees provided for final fields. That is the only way to write concurrent code that is demonstrably correct and behaves reliably across all the different hardware platforms Java runs on. This is where the most subtle, difficult bugs hide if you don't understand the specification deeply. Ultimately, the Java Language Specification is more than just a rulebook. It's the definitive description of the language's guarantees, its behavior, its semantics. A thorough understanding empowers you. It allows you to write code that isn't just functional, but is provably correct, performant, and future-proof. It lets you anticipate edge cases, design truly resilient systems, and genuinely master the Java platform.
Wow, what a journey. From those tiny Unicode characters making up your code, all the way to the incredibly intricate dance of threads in the Java memory model.
Oh.
We've really taken a comprehensive deep dive into the Java Language Specification, 24th edition.
We really have. We've uncovered the essence of Java's lexical structure, those critical distinctions in its type system, the power and, yes, the pitfalls of generics like heat pollution. We looked at the precise control flow mechanisms, including the new patterns, and dug into those foundational guarantees of the Java memory model.
So what does this all mean for you, the listener? You should now possess a far deeper, more nuanced understanding of Java's definitive rulebook. And this isn't just theory, right? It's the bedrock, the foundation for truly mastering Java, for tackling complex designs, or even for acing those really advanced interviews.
Absolutely. So maybe a provocative thought to leave you with, given the incredible precision and the focus on robustness that we've seen detailed throughout the JLS, what surprising design choices do you think might shape the next generation of Java? And how will the language continue to balance that crucial tension between developer productivity and rigorous safety in an ever-evolving tech landscape?
Something to ponder. We definitely encourage you to revisit this deep dive, reflect on these concepts, maybe even crack open the JLS PDF yourself for specific chapters that resonate with what you're working on right now. Until next time, keep digging deep and keep building amazing things with Java.